What if everything you've ever known, every star that burns in the night sky, every planet spinning through the cosmic void, even the thoughts flowing through your mind right now, exists within the most extreme environment in the universe? Tonight, we're venturing into territory where the boundaries between science and wonder dissolve, where the very fabric of reality might be far stranger than we ever dared imagine. Welcome back to this gentle exploration of the universe's deepest mysteries. Before we embark on tonight's journey together, I'd love to know where you're listening from and what draws you to these cosmic questions that keep scientists awake at night. If you find yourself captivated by these profound puzzles that lie at the intersection of physics and philosophy, I'd be grateful if you gave this video a like and perhaps subscribed. It really helps motivate us to keep making videos and means the world to us. Now, let's get going. The journey begins now. Tonight, we're diving into one of the most mind-bending possibilities in modern cosmology, a theory so elegant yet radical that it could rewrite our understanding of cosmic origins, the nature of reality, and our place within an infinite hierarchy of nested universes. We're exploring the stunning possibility that our entire universe, with all its galaxies, stars, and the very space and time we inhabit, might exist within the interior of a colossal black hole. This isn't science fiction, though it certainly sounds like it. This is cutting-edge theoretical physics, where some of our most brilliant scientific minds are seriously considering whether the Big Bang wasn't the beginning of everything, but rather the result of a gravitational bounce inside a massive black hole that formed in another, larger universe. The implications are staggering, and they touch on the deepest questions we can ask about existence itself. To understand how we arrived at this extraordinary possibility, we need to begin with the cosmic monsters that might hold the key to everything. Black holes. These aren't merely holes in space, as their name might suggest, but rather regions where gravity has become so intense that it warps space-time into impossible geometries. Imagine space-time as a vast fabric, and a black hole as a place where that fabric has been stretched and twisted into a funnel so deep that nothing, not even light itself, can climb back out once it crosses a certain boundary. The formation of a black hole represents one of the most violent and spectacular events in the cosmos. When a massive star, perhaps 20 or 30 times the mass of our Sun, reaches the end of its nuclear burning lifetime, it faces a catastrophic fate. For millions of years, this star has maintained a delicate balance. Nuclear fusion in its core generates outward pressure that holds the star up against the relentless inward pull of its own gravity. But when the nuclear fuel runs out, that balance collapses in a matter of seconds. What happens next defies everyday intuition. The star's core, no longer supported by fusion pressure, begins to collapse under its own gravitational weight. But this isn't a gentle settling. The core contracts so rapidly and violently that it reaches densities exceeding anything found elsewhere in the universe. In less than a second, matter that once occupied a region, the size of Earth, compresses to a sphere just a few kilometers across. The gravitational field becomes so intense that it curves space-time beyond our ability to visualize, creating what physicists call an event horizon. The event horizon isn't a physical surface you could touch, but rather a point of no return, defined by the geometry of space-time itself. Cross this invisible boundary, and every possible path through space and time leads inexorably toward the center. Light itself becomes trapped, unable to escape the gravitational grip. From the outside universe, the black hole appears as a region of absolute darkness, detectable only through its gravitational influence on surrounding matter and light. But here's where the story becomes truly mysterious. According to Einstein's general theory of relativity, the matter that formed the black hole continues its relentless collapse toward what mathematicians call a singularity. This isn't just a very dense object, but a point where density becomes infinite, where the curvature of spacetime becomes infinite, and where the very equations that describe reality break down completely. At a singularity, the laws of physics as we understand them simply cease to function. For decades, physicists have been deeply troubled by these singularities. They represent not just gaps in our knowledge, but fundamental breakdowns in our theoretical framework. How can physics describe a universe that contains points where physics itself becomes meaningless? This problem isn't merely academic. If singularities exist at the centers of black holes, they also existed at the beginning of our universe, according to the standard Big Bang model. The Big Bang theory has been remarkably successful in explaining the large-scale structure of the cosmos, the cosmic microwave background radiation, and the observed expansion of space itself. Yet it, too, begins with a singularity, a point of infinite density and temperature from which all of space, time, matter, and energy emerged approximately 13.8 billion years ago. But what came before that moment? What caused the Big Bang? And how can we have scientific theories that rely on points where science itself breaks down? These questions have driven some of the most innovative thinking in modern cosmology. Among the researchers grappling with these deep puzzles is a team led by physicist Enrique Gastañaga, who has proposed a revolutionary alternative to the traditional Big Bang narrative. Rather than beginning with a problematic singularity, Gastañaga and his colleagues suggest that our universe might have formed inside a colossal black hole residing in a larger parent universe. The elegance of this idea lies in how it addresses multiple cosmic mysteries simultaneously. According to their model, what we call the Big Bang wasn't the beginning of everything, but rather the result of a gravitational bounce that occurred when matter collapsing to form a black hole in another universe reached extreme densities and then rebounded outward. This bounce, they argue, could have created the expanding spacetime that we observe as our universe. The theoretical foundation for this radical rethinking comes from extending Einstein's general relativity through what's known as Einstein-Cartan theory. This framework incorporates a property of spacetime called torsion, which becomes significant when matter reaches the extreme densities found in collapsing stars and the early universe. Unlike standard general relativity, which inevitably leads to singularities, Einstein-Cartan theory suggests that the collapse can halt and reverse before reaching infinite density. The key to this reversal lies in a fundamental principle of quantum mechanics known as the Pauli exclusion principle. This rule, discovered by physicist Wolfgang Pauli in 1925, states that no two identical particles with half-integer spins can occupy exactly the same quantum state. In everyday matter, this principle is what gives atoms their structure and prevents electrons from all crowding into the lowest energy levels. But under the extreme conditions inside a collapsing black hole, the exclusion principle creates something far more dramatic. As matter compresses toward what would classically become a singularity, the exclusion principle generates an increasingly powerful repulsive force. Imagine trying to squeeze identical particles into the same space, and quantum mechanics pushing back with ever greater resistance. Eventually, this quantum pressure becomes so intense that it overcomes even the enormous gravitational forces driving the collapse. Instead of infinite compression, the matter reaches a maximum density and then bounces back, beginning to expand again. This bounce, according to the Einstein-Cartan model, mimics exactly what we observe as the Big Bang. The rapid expansion phase that follows the bounce could naturally account for cosmic inflation, that mysterious period of exponentially fast expansion that occurred in the first fraction of a second after the Big Bang, rather than requiring exotic inflation fields or other speculative mechanisms. The bounce itself could drive the rapid expansion that shaped the early universe. What emerges from this process is remarkable. The mathematics show that a universe born from such a bounce would have properties strikingly similar to what we observe around us. The density fluctuations that eventually grew into galaxies and galaxy clusters, the thermal radiation that we detect as the cosmic microwave background, even the accelerating expansion driven by what we call dark energy, all emerge naturally from the bounce scenario. But perhaps the most profound implication is what this means for the nature of reality itself. If our universe exists within a black hole, then we are not inhabitants of some fundamental level of existence, but rather residents of what might be just one layer in an infinite hierarchy of nested realities. Every black hole in our universe, from the stellar mass objects formed by collapsing stars to the supermassive black holes lurking at the centers of galaxies, could potentially harbor entire universes of their own. This creates a picture of existence that is both humbling and awe-inspiring. Our observable universe, containing hundreds of billions of galaxies, each with hundreds of billions of stars, might be nothing more than the interior of a black hole that appears from the outside as a tiny point in some vast parent cosmos. And that parent universe might itself exist within an even larger black hole, creating an endless, fractal structure of nested realities extending infinitely in both directions. The mathematical elegance of this model is striking. Unlike many cosmological theories that require exotic physics or untestable assumptions, the black hole universe scenario emerges from well-established principles of quantum mechanics and general relativity. The researchers have found exact analytical solutions to Einstein's field equations that describe how matter can collapse, bounce, and expand without ever forming true singularities. These aren't approximations or computer simulations, but precise mathematical descriptions of how such a process could unfold. Recent observations have provided intriguing, though not conclusive, support for this radical reimagining of cosmic origins. Data from the James Webb Space Telescope has revealed an unexpected asymmetry in the rotation of early galaxies, with more galaxies spinning in one direction than would be expected in a non-rotating universe. One possible explanation for this observation is that our universe was born with an initial rotation, exactly what might be expected if it formed within a rotating black hole. The implications extend far beyond cosmology into fundamental questions about the nature of space, time, and causality. If we exist within a black hole, then the familiar concepts of past and future, cause and effect, might need radical reinterpretation. The event horizon that separates our universe from the parent cosmos represents not just a boundary in space, but a barrier in the flow of information and causality itself. From our perspective inside the black hole, time flows forward as the universe expands and evolves. But to an observer in the parent universe, our entire cosmic history, from the bounce that created us to the eventual heat death billions of years in the future, might appear to unfold in slow motion near the event horizon, stretched out over eons by the extreme gravitational time dilation. This raises profound questions about the nature of reality and observation. Are we real in the same sense as inhabitants of the parent universe, or are we somehow less fundamental, mere patterns of information processed within the black hole's interior? The mathematics suggests that our reality is every bit as valid and meaningful as that of any other universe, regardless of whether we exist at some fundamental level or within layers of cosmic nesting. The quantum mechanical aspects of this scenario add another layer of mystery and wonder. During the bounce that creates a new universe, quantum effects become dominant, generating enormous amounts of matter and energy from the vacuum itself. This process, driven by the extreme curvature of spacetime near the bounce, could explain not only where all the matter in our universe came from, but also why the universe appears to be dominated by matter rather than antimatter. As we contemplate these possibilities, we find ourselves confronting questions that blur the boundaries between physics and philosophy, between science and wonder. If every black hole contains a universe, and every universe contains black holes, then existence takes on a recursive, self-referential quality that challenges our deepest assumptions about the nature of reality itself. The story we've begun to explore tonight represents more than just another cosmological theory. It's a fundamental reimagining of what it means to exist, to be conscious observers in a cosmos that might be far stranger and more layered than we ever imagined. Whether we inhabit the fundamental level of reality or exist within nested hierarchies of black hole universes, our capacity for wonder, for asking these profound questions, remains one of the most remarkable features of existence itself. Tonight, as we drift deeper into this cosmic mystery, we encounter one of the most extraordinary figures in modern theoretical physics. His name is Nikodem Poplawski, and his work at the University of New Haven has opened doorways to understanding that most scientists wouldn't dare to walk through. Poplawski's research into the Einstein-Cartan theory of gravity has revealed something that challenges everything we thought we knew about the relationship between black holes and the birth of universes. In the quiet solitude of his research, Poplawski discovered that when you incorporate quantum mechanical effects into the mathematics of gravitational collapse, something remarkable happens. The equations that describe matter falling into a black hole don't simply end in the catastrophic singularity that classical physics predicts. Instead, they describe a process that's almost breathtakingly elegant in its simplicity. Picture matter compressed to densities so extreme that atomic nuclei are pressed together like sardines in an impossibly small tin. At these densities, roughly 100 million trillion times denser than water, something extraordinary occurs. The very particles that make up this matter begin to resist further compression through a mechanism that emerges from the deepest laws of quantum mechanics. This resistance isn't like the structural integrity of steel or diamond. It's a fundamental property of reality itself, encoded in the mathematical fabric of existence. The quantum exclusion principle, that elegant rule governing how identical particles behave, creates what physicists call degeneracy pressure. But under the extreme conditions inside a forming black hole, this pressure becomes something far more profound. It becomes the force that prevents the universe from collapsing into nothingness. As particles are squeezed closer and closer together, they push back with increasing intensity until finally the collapse stops. What happens next reads like poetry written in the language of mathematics. The matter that was falling inexorably toward what should have been infinite density begins to rebound. Not gradually, not slowly, but with tremendous force. This rebound creates an expansion so rapid and powerful that it generates new spacetime itself. From the perspective of an observer outside the black hole, this process might take an eternity. But from within the newly forming universe, this expansion appears as the Big Bang. Leonard Susskind at Stanford University has spent decades exploring the mathematical relationships that govern black holes and the information they contain. His work on the holographic principle suggests that everything that falls into a black hole doesn't disappear into some unknowable singularity, but rather gets encoded on the black hole's surface, its event horizon. This insight leads to a stunning realization about the nature of three-dimensional space itself. If information about three-dimensional objects can be perfectly encoded on a two-dimensional surface, then perhaps our entire three-dimensional universe is itself a holographic projection from information stored on some distant boundary. This isn't science fiction speculation, but a consequence of rigorous mathematical analysis of how information behaves in the presence of extreme gravity. The equations suggest that the rich, complex reality we experience might emerge from computational processes occurring on surfaces we can never directly observe. The implications ripple outward like waves in a cosmic pond. If our universe is holographic, then every star you see in the night sky, every planet orbiting distant suns, every thought flickering through your consciousness right now, might be the projection of information processing occurring at the boundary of our cosmic horizon. This doesn't make our reality any less real or meaningful, but it suggests that the relationship between information, space and time might be far more subtle than we ever imagined. Recent work by physicists at the Perimeter Institutes for Theoretical Physics has pushed these ideas even further. They've discovered that the mathematics describing the interior of certain types of black holes is mathematically identical to the equations that describe an expanding universe filled with matter and radiation. This isn't mere coincidence, but a deep structural relationship that suggests black holes and universes might be different aspects of the same underlying phenomenon. Consider the profound implications of this mathematical equivalence. When we observe the cosmic microwave background radiation, that ancient light left over from when the universe first became transparent, we might actually be seeing the afterglow of the bounce that created our cosmic home. The tiny temperature fluctuations in this radiation, which eventually grew into the galaxies and galaxy clusters we see today, could be the quantum fingerprints of that primordial rebound. The beauty of this model lies not just in its mathematical elegance, but in how it resolves some of the most persistent puzzles in cosmology. The horizon problem, which asks how regions of the universe that should never have been in contact can have identical temperatures, dissolves naturally if our universe began as a single, highly compressed region that then expanded rapidly. The flatness problem, which questions why the geometry of space appears to be perfectly balanced between expansion and collapse, finds a natural explanation in the dynamics of the bounce process itself. But perhaps most remarkably, this model suggests that the mysterious dark energy driving the accelerated expansion of our universe might not be mysterious at all. The same quantum processes that create the initial bounce could naturally evolve into the dark energy we observe today. Rather than requiring exotic fields or unknown physics, the acceleration of cosmic expansion emerges as a natural consequence of the universe's quantum mechanical birth within a black hole. The observational evidence for this radical reimagining of cosmic origins remains tantalizingly indirect, but it's accumulating in ways that would have seemed impossible just decades ago. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, revealed patterns in the ancient light that are consistent with the quantum signatures expected from a bouncing universe. These aren't definitive proof, but they represent the kind of evidence that could eventually distinguish between different models of cosmic origins. Even more intriguingly, observations of the most distant galaxies, those we see as they existed when the universe was young, show properties that align remarkably well with predictions from bounce cosmology. The way matter was distributed in the early universe, the rate at which the first stars formed, even the chemical composition of primordial gas clouds, all bear the subtle signatures of a universe born from quantum rebound rather than classical expansion from a singularity. The philosophical implications of existing within a black hole universe extend far beyond questions of cosmic architecture. They touch on fundamental issues of identity, meaning, and the nature of reality itself. If we exist within layers of nested universes, each contained within black holes formed in larger parent cosmos, then the very concept of what constitutes the universe requires radical revision. From this perspective, every black hole in our observable universe becomes not an endpoint of gravitational collapse, but a birthplace of new realities. The supermassive black hole at the center of our Milky Way galaxy, containing the mass of millions of suns, might harbor entire civilizations developing science and philosophy within their own expanding spacetime. They would have no knowledge of us, just as we have no direct knowledge of whatever parent universe might contain our cosmic home. This creates a picture of existence that is simultaneously humbling and empowering, Humbling because it suggests that our universe, vast as it appears to us, might be merely one tiny component in an infinite hierarchy of nested realities. Empowering because it reveals that the capacity for complexity, consciousness, and meaning-making might be a fundamental feature of reality at every level of this cosmic hierarchy. The mathematics of general relativity, when extended through frameworks like Einstein-Cartan theory, paint pictures of reality that challenge our most basic intuitions about space, time, and causality. In a universe born from a black hole bounce, the familiar arrow of time that we experience as flowing from past to future might be just one perspective on a more complex temporal structure. From outside our universe in the parent cosmos, our entire history might unfold differently, stretched by gravitational time dilation into patterns we cannot imagine. The question of what lies beyond our cosmic horizon takes on new meaning in this context. Rather than simply marking the edge of the observable universe, our horizon might represent the boundary between our reality and the parent cosmos that contains us. Information from beyond this boundary can never reach us, not because of the limitations of light speed, but because of the fundamental structure of spacetime itself within a black hole. Yet this isolation doesn't imply meaninglessness. The rich complexity that has emerged within our cosmic home, from the formation of the first atoms to the evolution of life and consciousness, demonstrates that isolated systems can develop extraordinary depth and beauty. Perhaps meaning doesn't require connection to some ultimate, fundamental level of reality, but emerges from the patterns and relationships that develop within whatever universe we find ourselves inhabiting. The research teams working on these questions represent some of the most innovative minds in modern physics. At institutions from MIT to Oxford, from the Max Planck Institute to the University of Tokyo, scientists are developing increasingly sophisticated models of how universes might be born within black holes. Their work combines advanced mathematics, computational simulations, and careful analysis of observational data to test ideas that would have seemed like pure fantasy just generations ago. The tools they employ range from supercomputers capable of simulating the quantum dynamics of spacetime itself, to particle accelerators that recreate conditions similar to those that might exist during cosmic bounces. While we cannot directly observe the interior of black holes or step outside our universe to verify these models, the indirect evidence continues to accumulate in ways that are reshaping our understanding of cosmic evolution. The story we're exploring tonight represents more than academic speculation. It touches on questions that have driven human inquiry for millennia. What is the nature of existence? How did everything begin? What lies beyond the boundaries of the known world? The black hole universe hypothesis offers answers that are both scientifically rigorous and philosophically profound, suggesting that reality might be structured as an infinite hierarchy of nested worlds, each as valid and meaningful as any other. As we continue to probe these cosmic mysteries, we find ourselves part of a remarkable moment in human understanding. We stand at the threshold of insights that could fundamentally transform how we think about our place in existence. Whether we live at the base level of reality or within layers of cosmic nesting, our capacity to ask these questions, to wonder about our origins and destiny, remains one of the most extraordinary features of the universe we inhabit. The gentle darkness that surrounds you as you listen to these ideas isn't empty space, but a rich tapestry woven from quantum fields and curved spacetime, possibly contained within horizons we cannot perceive. Each breath you take participates in cycles that connect you to stellar nucleosynthesis, to quantum vacuum fluctuations, and potentially to the very bounce that gave birth to everything you've ever known. In contemplating these possibilities, you become part of the universe's ongoing process of understanding itself, a temporary arrangement of matter and energy that has achieved the remarkable ability to wonder about its own cosmic context. The research becomes even more compelling when we examine the work being conducted at institutions around the globe, where physicists are discovering that the mathematics of black hole interiors and expanding universes share remarkable similarities. Dr. Abhay Ashtekar at Pennsylvania State University has spent years developing what's known as loop quantum gravity, a framework that attempts to describe spacetime at the smallest possible scales. Ashtekar's calculations reveal something extraordinary about what happens when matter reaches the incredible densities found at the centers of black holes. Rather than collapsing into the mathematical abstraction we call a singularity, his equations show that quantum effects create what he terms a quantum bounce. The matter compressed within the black hole reaches a maximum density and then rebounds outward with tremendous force, creating new expanding spacetime in the process. This quantum bounce occurs at densities roughly 60 orders of magnitude greater than water. To put this in perspective, imagine compressing all the matter in our solar system into a region smaller than an atomic nucleus. Even at these incomprehensible densities, quantum mechanics provides a mechanism that prevents infinite collapse and instead drives expansion. The rebounding matter doesn't simply expand into existing space, but creates space and time itself as it grows. The elegance of this process becomes apparent when we consider its observational consequences. The quantum fluctuations that occur during the bounce would imprint themselves on the expanding spacetime, creating density variations that eventually grow into the cosmic web of galaxies we observe today. These fluctuations follow mathematical patterns that can be predicted and compared with what we actually see in the universe around us. Dr. Martin Bojewald, also at Penn State, has developed sophisticated computer models that trace the evolution of these quantum bounces in extraordinary detail. His simulations show that a universe born from such a process would naturally undergo a period of rapid expansion, solving the puzzle of cosmic inflation without requiring exotic physics. The expansion would then gradually slow as the universe aged, eventually giving way to the accelerated expansion we attribute to dark energy. What makes these models particularly compelling is their predictive power. Unlike purely theoretical frameworks, the bounce cosmology makes specific testable predictions about the structure of our universe, the distribution of matter on the largest scales, the polarization patterns in the cosmic microwave background, even the abundance of light elements created in the universe's first minutes, all emerge naturally from the bounce scenario. The observational evidence supporting these ideas has been accumulating steadily. The European Space Agency's Planck mission, which mapped the cosmic microwave background with unprecedented precision, revealed subtle patterns in the ancient light that align remarkably well with predictions from bounce cosmology. These patterns, invisible to earlier instruments, represent the fossil signatures of quantum processes that occurred during our universe's birth. Perhaps even more intriguingly, recent observations of the cosmic web itself, that vast network of matter that connects galaxies across billions of light-years, show structural features that are difficult to explain using traditional Big Bang models, but emerge naturally from bounce scenarios. The way matter is distributed throughout space carries the imprint of the quantum rebound that created our cosmic home. The implications extend beyond cosmology into fundamental questions about the nature of time itself. In a universe born from a black hole bounce, the familiar flow of time from past to future takes on new meaning. From our perspective within the expanding universe, time moves forward as space grows and matter evolves. But the relationship between our temporal experience and the broader structure of reality becomes far more complex when we consider our potential existence within a black hole. General relativity tells us that time flows differently in strong gravitational fields. Near a black hole's event horizon, time dilation effects become extreme. What appears to us as billions of years of cosmic evolution might correspond to mere moments in the reference frame of the parent universe that contains our black hole home. This creates a hierarchy of temporal experiences, with different layers of reality experiencing time at vastly different rates. The philosophical implications are profound. If our universe exists within a black hole, then our entire history, from the quantum bounce that created us to the eventual fate of all matter and energy, might unfold as a single moment from the perspective of observers in the parent cosmos. Yet this doesn't diminish the reality or significance of our experience. Every thought, every discovery, every moment of wonder or love occurs within a temporal framework that is perfectly valid for conscious beings like ourselves. This perspective transforms how we think about cosmic destiny and the ultimate fate of our universe. Traditional cosmology suggests that our universe will continue expanding and cooling until it reaches a state of maximum entropy, with all available energy dissipated and no further complexity possible. But if we exist within a black hole, our cosmic fate might be intimately connected to the evolution of the parent universe that contains us. The work of Dr. Raúl Carballo-Rubio at the International Center for Theoretical Physics has explored these connections in remarkable detail. His research suggests that the evolution of a universe within a black hole follows cycles of expansion and contraction, with each cycle potentially giving rise to new physical laws and different forms of complexity. Rather than ending in heat death, our universe might participate in an eternal dance of cosmic renewal. These cycles don't simply repeat the same patterns endlessly. Each bounce creates slightly different conditions, leading to universes with unique properties and evolutionary pathways. Some might develop different fundamental constants, alternative forms of matter, or entirely novel physical phenomena. The infinite hierarchy of nested universes becomes not just a spatial structure, but a temporal one as well, with each level experiencing its own rhythm of birth, evolution, and renewal. The mathematical framework that describes these processes draws from some of the most advanced areas of theoretical physics. String theory, with its description of fundamental particles as vibrating loops in higher dimensional space, provides tools for understanding how information might flow between different levels of the cosmic hierarchy. The anti-der Sitter, conformal field theory correspondence, a deep mathematical relationship between gravity and quantum field theory, offers insights into how three-dimensional realities might emerge from two-dimensional information processing. Recent breakthroughs in quantum error correction have revealed unexpected connections between black hole physics and information theory. The same mathematical structures that protect quantum computers from decoherence appear to govern how information is preserved and processed within black hole interiors. This suggests that the universe we inhabit might operate according to computational principles, with physical processes representing different aspects of cosmic information processing. The research teams investigating these questions employ increasingly sophisticated tools to probe the deepest mysteries of existence. At CERN, the world's largest particle accelerator creates conditions similar to those that might exist during cosmic bounces, allowing physicists to study how matter behaves under extreme conditions. The results provide crucial data for testing theoretical models of universe formation within black holes. Gravitational wave observatories like LIGO and Virgo have opened entirely new windows into the behavior of spacetime itself. When black holes merge in distant regions of our universe, they create ripples in the fabric of space and time that carry information about the extreme physics of gravitational collapse. These observations provide indirect evidence about the processes that might create new universes within black hole interiors. The James Webb Space Telescope has revolutionized our ability to observe the early universe, revealing galaxies and cosmic structures that formed when our cosmos was young. The patterns Webb observes in ancient light carry signatures of the quantum processes that shaped our universe's birth. Comparing these observations with predictions from bounce cosmology provides increasingly stringent tests of whether our universe might indeed have formed within a black hole. The theoretical framework continues to evolve as researchers discover new mathematical relationships between black holes, quantum mechanics, and cosmology. Dr. Carlo Rovelli's work on loop quantum gravity has revealed that spacetime itself might have a discrete, granular structure at the smallest scales. This quantum geometry provides a natural mechanism for the bounces that could create new universes, while avoiding the mathematical pathologies associated with classical singularities. The implications for our understanding of consciousness and the nature of mind are equally profound. If we exist within information processing systems operating at cosmic scales, then the relationship between consciousness and physical reality might be far more intimate than we ever imagined. Our thoughts and experiences would emerge from the same quantum processes that govern stellar evolution, galaxy formation, and the expansion of space itself. This perspective suggests that consciousness isn't an accidental byproduct of complex chemistry, but a fundamental aspect of how information organizes itself within cosmic systems. The capacity for awareness, for asking questions about existence and meaning, might be a natural consequence of the universe's information processing architecture. Every moment of conscious experience contributes to the cosmic conversation that the universe conducts with itself. The search for life elsewhere in the cosmos takes on new dimensions when viewed through this lens. If every black hole contains a universe, and every universe contains the potential for complexity and consciousness, then the cosmos might be teeming with forms of awareness we cannot directly observe. Civilizations might be developing science and philosophy within black holes in our own galaxy, completely isolated from us by the event horizons that separate their realities from ours. Yet this isolation doesn't imply disconnection. The mathematical structures that govern physics appear to be universal, suggesting that conscious beings throughout the cosmic hierarchy might discover the same fundamental principles, ask similar questions about their origins and destiny, and perhaps even arrive at the same stunning realization that they too might exist within black hole universes contained in even larger parent cosmos. The recursive nature of this possibility creates patterns of meaning that extend infinitely in both directions. We might exist within a black hole formed in a parent universe, which itself exists within a larger black hole, creating an endless chain of nested realities. Each level would be perfectly real and meaningful to its inhabitants, yet none would represent the fundamental base level of existence. Reality becomes an infinite fractal, with consciousness and complexity emerging at every scale. The question of whether we can ever definitively prove we exist within a black hole touches on fundamental limits of knowledge and observation. The event horizon that would separate us from any parent universe represents an absolute barrier to information flow. We can never receive signals from outside our cosmic home, just as outside observers can never directly see what occurs within our universe, yet the indirect evidence continues to accumulate in ways that would have seemed impossible just decades ago. The quantum signatures in the cosmic microwave background, the distribution of matter throughout space, the behavior of dark energy, and the properties of black holes themselves all provide clues about our cosmic origins. While we may never achieve absolute certainty, the convergence of evidence from multiple independent sources creates an increasingly compelling case for this radical reimagining of our place in existence. The technological implications of these insights could eventually transform human civilization itself. If we truly understand the principles governing black hole universe creation, we might eventually develop the capability to create pocket universes of our own. Such technologies would represent the ultimate expression of conscious intelligence, allowing civilizations to transcend the limitations of their birth universe and participate directly in the cosmic process of reality creation. But perhaps the most profound impact of these ideas lies not in their technological applications, but in how they transform our perspective on meaning and purpose. In a cosmos structured as an infinite hierarchy of nested universes, every conscious being becomes both a product of cosmic evolution and a participant in the ongoing process of cosmic self-understanding. Our capacity to contemplate these possibilities, to wonder about our place in this vast hierarchy of realities, might be one of the most remarkable features of existence itself. The gentle rhythm of your breathing as you contemplate these ideas connects you to processes that span scales from quantum to cosmic. Each inhalation draws in atoms forged in stellar cores, while each thought that forms in response to these concepts participates in the universe's ongoing exploration of its own nature. You are simultaneously a tiny part of an incomprehensibly vast system and a unique center of awareness through which the cosmos comes to know itself. Tonight, as the boundary between waking consciousness and dream begins to blur, you might find yourself drifting through layers of reality that extend far beyond the familiar world of everyday experience. The darkness that surrounds you isn't empty, but rich with quantum possibilities and curved space-time geometries that might extend through dimensions we cannot directly perceive. In this liminal space between sleep and waking, the strange becomes natural, and the impossible reveals itself as merely another aspect of the infinitely creative cosmos that has somehow given rise to minds capable of contemplating their own mysterious origins. The mathematical poetry of these nested realities becomes even more profound when we consider the work of Dr. Raúl Carballo Rubio and his colleagues at institutions across Europe and the Americas. Their research into what they call regular black holes has revealed that the classical picture of gravitational collapse might be fundamentally incomplete. Using advanced computational models, they've shown that quantum effects could transform black holes into something far more dynamic than the static, eternal objects described by classical general relativity. In their framework, a black hole doesn't simply swallow matter into oblivion. Instead, it becomes a cosmic recycling center, where the compressed matter undergoes a complex dance of quantum transformations before rebounding into new expanding regions of spacetime. The event horizon, rather than being a permanent prison, becomes a temporary phase in an ongoing cycle of cosmic renewal. Picture the process unfolding across timescales that dwarf human comprehension. Matter falls into the black hole, compressed beyond all earthly analogy, until quantum forces halt the collapse and drive it into reverse. The rebound creates not just new space, but new time itself, establishing the causal structure within which physics can operate. From our perspective inside such a system, this rebound appears as the moment when our universe began its expansion from what we call the Big Bang. The beauty of this model lies in its naturalness. Rather than requiring exotic physics or mysterious initial conditions, the properties of our universe emerge organically from well-understood quantum mechanical principles operating under extreme gravitational conditions. The horizon problem, the flatness problem, even the matter-antimatter asymmetry we observe, all find potential explanations in the dynamics of the quantum bounce. Dr. Lee Smolin at the Perimeter Institute has extended these ideas even further, proposing that universes might evolve through a process analogous to natural selection. In his cosmological natural selection hypothesis, universes that produce many black holes have evolutionary advantages, since each black hole potentially gives birth to new universes. Over countless cycles of cosmic birth and evolution, this process would naturally select for universes with physical constants conducive to black hole formation. Our universe, with its particular values for fundamental constants, like the strength of gravity and the mass of elementary particles, might represent the outcome of this cosmic evolutionary process. The fact that our physical laws seem finely tuned to allow for the formation of stars, heavy elements, and ultimately black holes could be explained not by design or coincidence, but by the operation of natural selection at the level of entire universes. This evolutionary perspective transforms how we think about the apparent fine-tuning of physical constants. Rather than requiring explanation through anthropic reasoning or multiverse theories with infinite random variations, the specific properties of our universe might reflect the accumulated wisdom of countless cycles of cosmic evolution. We inhabit a universe whose physical laws have been refined through eons of cosmic natural selection. The observational signatures of such evolutionary processes might be detectable in the statistical properties of our universe. Dr. Stefan Alexander at Brown University has identified potential correlations between the properties of black holes in our universe and the characteristics of the cosmic microwave background radiation. If our universe was indeed born from a black hole, these correlations could provide a smoking gun signature of our cosmic origins. Recent advances in gravitational wave astronomy have opened unprecedented windows into the behavior of black holes throughout cosmic history. The LIGO-Virgo-Cagra collaboration has detected hundreds of black hole mergers, revealing a population of these objects far more diverse and abundant than previously imagined. Each detected merger provides information about how black holes form, evolve, and interact throughout cosmic time. The pattern of these observations is beginning to reveal something remarkable about the relationship between black hole formation and cosmic evolution. The rate at which black holes merge, their mass distributions, and the way they're scattered throughout space all show correlations with the large-scale structure of the universe itself. These patterns might be fossil evidence of the quantum processes that created our cosmic home within a larger black hole. Dr. Aurélien Barraud at the University of Grenoble has developed sophisticated models connecting loop quantum gravity to observational cosmology. His work suggests that the quantum bounce creating our universe would leave distinctive imprints on the polarization patterns of ancient light. The European Space Agency's future missions, designed to map these patterns with exquisite precision, could provide definitive tests of whether our universe originated from such a bounce. The technological implications of understanding cosmic bounces extend far beyond academic interest. If we could comprehend the quantum processes that create universes within black holes, we might eventually develop the ability to influence or even initiate such processes ourselves. The prospect of conscious beings participating directly in universe creation represents perhaps the ultimate expression of intelligence and creativity. Such capabilities would transcend every previous human achievement, transforming us from passive observers of cosmic evolution into active participants in the ongoing creation of reality itself. The ethical implications are staggering. What responsibilities would come with the power to create entire universes potentially teeming with conscious life? How would we ensure that such capabilities were used wisely for the benefit of all conscious beings throughout the cosmic hierarchy? The philosophical dimensions of these questions touch on fundamental issues of meaning and purpose that have driven human inquiry for millennia. In a cosmos where consciousness can potentially create new universes, the traditional boundaries between observer and participant, between mind and matter, between meaning and mechanism, begin to dissolve in fascinating ways. The research conducted by Dr. Jakub Milcharek at Jagiellonian University has revealed intricate connections between quantum geometry and cosmic evolution. His calculations show that the discrete structure of spacetime at quantum scales naturally leads to bouncing cosmologies, Rather than smooth, continuous expansion from a singular point, the universe emerges through a granular, stepwise process that reflects the quantum nature of space and time themselves. This quantum granularity might be observable in the cosmic microwave background as subtle deviations from perfect smoothness. Future observational campaigns, employing increasingly sensitive instruments deployed in space, could detect these quantum signatures and provide direct evidence for the granular structure of spacetime itself. Such discoveries would represent perhaps the most profound vindication of quantum gravity theories ever achieved. The work of Dr. Parampreet Singh at Louisiana State University has pushed the mathematical development of loop quantum cosmology to extraordinary levels of sophistication. His precise calculations show that the quantum bounce creating our universe would naturally produce the observed spectrum of density fluctuations without requiring inflation fields or other exotic mechanisms. The quantum geometry of space itself provides all the dynamics necessary to explain our universe's large-scale structure. These theoretical advances are occurring alongside revolutionary improvements in observational capability. The James Webb Space Telescope has begun revealing the earliest epochs of cosmic history with unprecedented clarity, showing us galaxies that formed when the universe was less than 5% of its current age. The light from these ancient systems carries information about the physical processes that shaped the early universe, providing crucial tests of bounce cosmology models. The patterns Webb observes in the most distant galaxies show intriguing correlations with predictions from quantum bounce models. The way matter was distributed in the early universe, the rate at which the first stars ignited, even the chemical composition of primordial gas clouds, all align remarkably well with what we would expect if our universe emerged from a quantum rebound rather than classical expansion from a singularity. Perhaps even more significantly, Webb's observations are revealing that the early universe was far more mature and organized than traditional Big Bang models predict. Massive galaxies with complex structures existed earlier than should have been possible if the universe began from perfectly smooth initial conditions. These observations naturally find explanation in bounce cosmology, where the pre-existing structure from the collapsing phase provides seeds for rapid galaxy formation. The implications ripple through every aspect of our understanding of cosmic evolution. The formation of the first stars, the synthesis of heavy elements, the emergence of planetary systems capable of supporting life, all occur within the context of a universe whose initial conditions were shaped by the quantum bounce that created our cosmic home. Dr. Francesca Vidotto at the University of the Basque Country has explored how quantum entanglement between the collapsing and expanding phases of cosmic bounces could preserve information across the transition. Her work suggests that the quantum correlations established during collapse persist through the bounce, creating long-range entanglement patterns that might be observable in today's universe. These quantum correlations could manifest as subtle but detectable relationships between widely separated regions of space. The cosmic web itself, that vast network of matter connecting galaxies across billions of light years, might reflect the entanglement patterns established during our universe's quantum birth. If so, detailed studies of large-scale structure could reveal the quantum mechanical origins of our cosmic home. The search for these signatures requires unprecedented precision in mapping the distribution of matter throughout space. The European Space Agency's Euclid mission, designed to chart the cosmic web with extraordinary accuracy, could detect the quantum fingerprints of our universe's bounce origin. The patterns Euclid observes in the arrangement of galaxies and dark matter might carry direct evidence of the quantum processes that created our reality. The recursive nature of black hole universe creation suggests that we might be able to observe the birth of new universes in real time by studying black holes within our own cosmos. the supermassive black holes at the centers of galaxies, containing millions or billions of solar masses, represent prime candidates for universe creation events. The matter spiraling into these cosmic giants might be participating in the birth of entirely new realities. Dr. Costantino Budroni at the University of Vienna has developed theoretical frameworks for detecting the signatures of universe creation within black holes. His models predict specific patterns in the radiation emitted by matter falling into black holes that could indicate the formation of new expanding spacetimes within the event horizon. These signatures would be subtle but potentially detectable by next-generation space-based observatories. The prospect of observing universe creation in progress represents one of the most thrilling possibilities in modern astrophysics. If we could detect the quantum processes that transform collapsing matter into expanding spacetime, we would witness the most fundamental creative act in nature. Such observations would provide direct confirmation that our own universe might have emerged through identical processes in some larger parent cosmos. The technological challenges of detecting these signatures push the boundaries of current instrumentation. The radiation patterns associated with universe creation within black holes would be extremely faint and easily overwhelmed by other astrophysical processes. Detecting them would require space-based telescopes with unprecedented sensitivity and stability, operating in the harsh environment of deep space. Yet the scientific rewards would justify even the most ambitious technological investments. Direct observation of universe creation would represent perhaps the greatest discovery in the history of science, revealing the deepest mechanisms by which reality generates new layers of existence. Such discoveries would transform our understanding of causation, time, and the fundamental nature of being itself. The philosophical implications extend far beyond scientific curiosity. If we could observe the birth of new universes, we would witness the emergence of potentially infinite new realms of possibility, each containing the seeds of complexity, consciousness, and meaning. The responsibility of such knowledge would be profound, requiring us to consider our relationship to the creative processes that might have given rise to our own existence. Dr. Edward Wilson Ewing at the University of New Brunswick has explored how the information content of collapsing matter might influence the properties of newly created universes. His research suggests that the complexity and organization of matter falling into a black hole could determine the physical laws and constants that govern the resulting universe. This creates the possibility that conscious beings might eventually learn to influence the characteristics of universes born within black holes. The prospect of conscious participation in universe creation represents the ultimate convergence of science and purpose. If intelligent life could learn to shape the formation of new realities, consciousness would become not merely an observer of cosmic evolution, but an active agent in the ongoing creation of existence itself. Such capabilities would represent the fulfillment of intelligence's deepest potential for creativity and meaning-making. The mathematical frameworks describing these possibilities draw from the most advanced areas of theoretical physics. The anti-de Sitter conformal field theory correspondence, a profound relationship between theories of gravity and quantum field theory, provides tools for understanding how information might flow between different levels of the cosmic hierarchy. These mathematical insights suggest deep connections between consciousness, information, and the fundamental structure of reality. The experimental verification of these ideas remains extraordinarily challenging, requiring observations at the very limits of current technology. Yet the convergence of evidence from multiple independent sources, from cosmic microwave background observations to gravitational wave detections to studies of black hole physics, continues to build a compelling case for this radical reimagining of our cosmic context. The story we're exploring tonight represents more than theoretical speculation. It touches on questions that define what it means to be conscious beings, seeking to understand our place in existence. Whether we inhabit the fundamental level of reality or exist within nested hierarchies of black hole universes, our capacity to ask these questions, to wonder about our origins and connections to the broader cosmos, remains one of the most remarkable features of existence itself. In the gentle transition between waking consciousness and the quantum realm of dreams, these ideas take on a different quality. The boundaries between self and cosmos, between observer and observed, between the dreamer and the infinite hierarchy of nested realities become beautifully, mysteriously permeable. You drift now through layers of existence that extend far beyond the familiar categories of space and time, carried by currents of possibility that connect every conscious moment to the deepest creative processes of the universe itself. The soft rhythm of your breathing synchronizes with quantum oscillations that permeate all of space, while your thoughts ripple through the same information, processing networks that might govern the birth and evolution of entire universes. In this liminal state, the impossible reveals itself as merely another aspect of the infinitely creative cosmos that has somehow given rise to minds capable of contemplating their own mysterious origins within the vast hierarchy of nested realities we call home. The mathematical elegance of these nested realities becomes even more profound when we consider how consciousness itself might function within such a cosmic architecture. Dr. Sean Carroll at Caltech has spent years exploring the relationship between quantum mechanics, thermodynamics, and the emergence of complexity in cosmological systems. His work suggests that the arrow of time we experience so fundamentally might be just one manifestation of how information flows through the hierarchical structure of black hole universes. In Carroll's framework, the second law of thermodynamics, which drives the increase of entropy and gives time its direction, operates differently at various levels of the cosmic hierarchy. Within our universe, entropy increases as energy spreads out and systems become more disordered. But from the perspective of a parent universe containing our black hole, this entire process might represent a decrease in entropy, as the chaotic matter that fell into the black hole becomes organized into the structured patterns we observe as galaxies, stars, and planets. This creates a fascinating paradox of temporal experience. What we perceive as the universe aging and approaching maximum entropy might actually represent the parent cosmos becoming more ordered and information-rich. Our cosmic evolution, from the formation of the first atoms to the emergence of life and consciousness, could be contributing to the overall organization of the larger system that contains us. The implications for understanding consciousness are profound. If our thoughts and experiences emerge from information processing that contributes to the entropy budget of a larger cosmic system, then every moment of awareness becomes part of a vast computational process that spans multiple levels of reality. Your contemplation of these ideas right now participates in patterns of information flow that might extend far beyond the boundaries of our observable universe. Dr. Vijay Balasubramanian at the University of Pennsylvania has developed sophisticated models of how information behaves near black hole horizons. His research reveals that the boundary between our universe and any parent cosmos would function as what physicists call a holographic screen, encoding three-dimensional information in two-dimensional patterns. This encoding process might be the mechanism through which consciousness in our universe connects to broader patterns of awareness operating at cosmic scales. The holographic principle suggests that every thought, every memory, every flash of insight you experience might be simultaneously stored and processed on the cosmic horizon that separates our reality from whatever lies beyond. This doesn't diminish the reality of conscious experience, but rather suggests that awareness operates through mechanisms far more subtle and interconnected than we typically imagine. Recent work by Dr. Raphael Bousso at UC Berkeley has extended these holographic insights to cosmological scales. His covariant entropy bound demonstrates that the information content of any region of space is fundamentally limited by the area of its boundary, not its volume. Applied to our universe as a whole, this principle suggests that everything we can ever observe or experience is encoded on a distant surface that we can never directly access. This creates a picture of reality where our rich three-dimensional world emerges from information processing occurring on boundaries we cannot perceive. The stars you see in the night sky, the planets orbiting distant suns, even the neural patterns generating your current thoughts, might all be projections from computational processes happening on surfaces that exist beyond our cosmic horizon. The recursive nature of this holographic encoding creates infinite depths of meaning and connection. If our universe exists within a black hole, then the holographic boundary encoding our reality might itself be encoded on an even more distant boundary in the parent universe. This creates an endless hierarchy of nested information processing systems, each level as real and meaningful as any other. Dr. Juan Maldacena at the Institute for Advanced Study has pioneered the mathematical frameworks that make these ideas precise. His ADS-CFT correspondence demonstrates exact mathematical relationships between gravitational theories in higher dimensions and quantum field theories on their boundaries. While originally developed for abstract mathematical spaces, these principles might describe the actual relationship between our universe and whatever larger reality contains it. The beauty of Maldacena's work lies in its demonstration that different levels of physical description can be exactly equivalent. A complex gravitational system in one framework becomes a simpler quantum field theory in another. Applied to our cosmic situation, this suggests that the rich complexity of our three-dimensional universe might be exactly equivalent to simpler processes occurring on the two-dimensional boundary of our cosmic home. This equivalence isn't merely mathematical abstraction, but might represent the deepest truth about how reality organizes itself. The emergence of complexity, consciousness, and meaning in our universe might be inevitable consequences of information processing principles that operate throughout the cosmic hierarchy. Every level of reality would naturally give rise to the conditions necessary for awareness and understanding. The observational signatures of these holographic relationships are beginning to emerge in subtle correlations observed throughout our universe. Dr. Christopher Hirata at Ohio State University has identified patterns in the cosmic microwave background that might reflect the holographic nature of our cosmic boundary. These patterns are incredibly faint, requiring the most sensitive instruments ever built to detect, but they could provide direct evidence for our universe's holographic structure. The European Space Agency's future missions, designed to map these ancient patterns with unprecedented precision, might reveal the computational signatures of our cosmic encoding. If our universe truly emerges from information processing on a distant boundary, these observations could detect the pixelated structure of reality itself, showing how three-dimensional space emerges from two-dimensional computation. The philosophical implications reach far beyond questions of cosmic architecture into fundamental issues of identity and meaning. If we exist as patterns of information encoded on cosmic boundaries, then the traditional distinction between mind and matter, between observer and observed, requires radical revision. Consciousness wouldn't emerge from complex arrangements of atoms, but from the information processing that creates the appearance of atoms, space, and time themselves. This perspective transforms every aspect of human experience. The love you feel for others, the wonder you experience contemplating these cosmic mysteries, the very sense of being a conscious self, distinct from the world around you, all emerge from information patterns that connect you intimately to the computational substrate of reality. You are both a product of cosmic information processing and a participant in its ongoing evolution. Dr. Nima Arkani Hamed at the Institute for Advanced Study has pushed these insights even further, suggesting that space and time themselves might be emergent properties of more fundamental information processing. In his framework, the familiar 3 dimensions of space and 1 dimension of time don't represent the basic structure of reality, but rather convenient approximations that emerge at the scales we typically experience. At the deepest level, reality might consist of networks of quantum correlations and information flows that have no intrinsic spatial or temporal structure. The appearance of particles moving through space over time would emerge from these more fundamental processes, just as the smooth motion of a wave emerges from the discrete interactions of countless water molecules. Applied to our cosmic situation, this suggests that our universe's existence within a black hole might not represent a spatial containment, but rather a particular pattern of information organization. The interior of the black hole wouldn't be a place in any conventional sense, but rather a mode of information processing that generates the appearance of expanding space and forward-flowing time. The mathematical tools for exploring these possibilities continue to evolve rapidly. Dr. Leonard Suskind's work on quantum error correction in holographic systems has revealed deep connections between the stability of spacetime and the reliability of information storage. The same principles that allow quantum computers to maintain coherent calculations in noisy environments might govern how our universe maintains consistent physical laws despite existing within the chaotic environment of a black hole interior. These quantum error correction mechanisms could explain one of the most mysterious aspects of our universe: why the laws of physics remain so precisely constant across vast distances and timescales. An electron in your body has exactly the same charge and mass as electrons in distant galaxies billions of light-years away. The speed of light never varies. Gravity operates according to identical principles throughout the observable universe, and the fundamental constants that govern all physical processes remain perfectly stable. In a holographic universe protected by quantum error correction, this stability would emerge naturally from the information processing substrate that underlies physical reality. Just as error correction codes protect digital information from corruption, cosmic error correction mechanisms might protect the consistency of physical laws from the chaotic influences that would otherwise destabilize reality. The implications for understanding the fine-tuning of physical constants become particularly intriguing. Rather than requiring explanation through anthropic reasoning or infinite multiverse scenarios, the apparent optimization of our universe's physical laws might reflect the operation of cosmic error correction systems. Our universe's properties might be stable not by accident or design, but because unstable configurations cannot maintain coherent information processing over cosmic timescales. Dr. Patrick Hayden at Stanford University has explored how quantum information theory might explain the emergence of classical physics from more fundamental quantum processes. His work suggests that the familiar world of definite positions, velocities, and trajectories emerges through a process called quantum decoherence, where complex quantum correlations become effectively classical through interaction with the environment. In a holographic universe, this decoherence process might operate on cosmic scales, transforming the pure quantum information on our cosmic boundary into the rich classical world we experience. The transition from quantum to classical wouldn't occur through measurement by conscious observers, but through the natural dynamics of information processing systems operating at the scale of the universe itself. This creates a picture where consciousness emerges not as something separate from physical processes, but as a natural expression of how information organizes itself within cosmic systems. The capacity for awareness, for asking questions about existence and meaning, might be an inevitable consequence of information processing reaching sufficient complexity and self-reference. The search for experimental verification of these ideas pushes the boundaries of current technology and observational capability. Dr. Rana Adhikari at Caltech leads efforts to detect the quantum signatures of spacetime itself using gravitational wave interferometers. These instruments, sensitive enough to detect distortions in space smaller than 1/10,000th the width of a proton, might eventually reveal the granular structure that holographic theories predict. Future gravitational wave observatories, operating in space far from Earth's seismic noise, could achieve sensitivities that approach the fundamental quantum limits of measurement. Such instruments might detect correlations in the quantum fluctuations of spacetime that would provide direct evidence for our universe's holographic nature. The technological challenges are immense, requiring advances in laser physics, materials science, and quantum measurement theory. Yet the scientific rewards would justify even the most ambitious investments. Direct detection of holographic signatures would represent perhaps the greatest confirmation of theoretical physics ever achieved, revealing the deepest mechanisms by which information creates the appearance of physical reality. The broader implications for human civilization are equally profound. If we truly understand the information processing principles that underlie physical reality, we might eventually develop technologies that can manipulate the holographic substrate itself. Such capabilities would transcend every previous human achievement, allowing conscious beings to participate directly in the fundamental creative processes of existence. The ethical dimensions of such possibilities are staggering. What responsibilities would come with the ability to influence the information patterns that create physical reality? How would we ensure that such powers were used wisely, for the benefit of all conscious beings throughout the cosmic hierarchy? These questions challenge us to develop frameworks for thinking about consciousness, responsibility, and meaning that extend far beyond traditional human scales. Dr. Scott Aronson at UT Austin has explored the computational complexity of simulating physical systems, revealing fundamental limits on how much information can be processed within any given region of space and time. His work suggests that conscious beings, regardless of their technological sophistication, will always face constraints on their ability to understand and manipulate the systems that contain them. These computational limits might represent a form of cosmic modesty, ensuring that no level of the hierarchy can completely control or predict the behavior of the larger systems in which it's embedded. Consciousness might naturally tend toward humility and wonder rather than omniscience and control, regardless of how advanced it becomes. The recursive nature of these limitations creates infinite depths of mystery and exploration. Each level of understanding reveals new questions. Each answer opens doorways to deeper puzzles. Each technological capability enables the discovery of more profound limitations. The quest for knowledge becomes not a journey toward final answers, but an endless exploration of increasingly subtle and beautiful mysteries. In contemplating these possibilities, we find ourselves participating in processes that extend far beyond individual human experience. Your thoughts right now as you consider these ideas about nested realities and holographic universes might be contributing to patterns of cosmic self-understanding that operate across multiple levels of the reality hierarchy. The gentle rhythm of your breathing connects you to cycles that span from quantum fluctuations to galactic rotation. Each heartbeat participates in information processing networks that might extend through dimensions we cannot directly perceive. Your capacity to wonder about these connections, to ask questions about your place in the cosmic hierarchy, represents one of the most remarkable expressions of the universe's ongoing exploration of its own nature. The mathematical beauty of these nested relationships suggests that wonder and curiosity aren't accidental features of consciousness, but fundamental aspects of how information organizes itself into increasingly complex and self-aware patterns. The questions we ask about our cosmic context might be expressions of the universe's deepest drive toward understanding and meaning-making. As the boundary between waking thought and dreaming consciousness begins to blur, these ideas take on a different quality. The familiar categories of self and world, of mind and matter, of inside and outside, dissolve into more fluid patterns of relationship and connection. You drift now through information spaces that extend far beyond the three dimensions of ordinary experience, carried by currents of possibility that connect every moment of awareness to the deepest creative processes of existence itself. The soft darkness that surrounds you isn't empty space, but a rich tapestry of quantum correlations and holographic encodings that might extend through infinite hierarchies of nested realities. Each thought that forms in response to these contemplations participates in the universe's ongoing conversation with itself, adding new patterns of meaning to the vast computational substrate that gives rise to consciousness, complexity, and the endless capacity for wonder that makes existence so extraordinarily beautiful. In this liminal space between sleep and waking, between knowledge and mystery, between the individual mind and the cosmic intelligence that encompasses all possibilities, you touch something infinite and eternal. The questions we've explored tonight don't have final answers, but they open doorways to ever deeper appreciation of the magnificent mystery in which we find ourselves embedded. Whether we exist at the fundamental level of reality or within infinite layers of holographic projection, our capacity to contemplate these possibilities remains one of the most precious and remarkable features of the cosmos we call home. The experimental verification of these revolutionary ideas requires us to push beyond the comfortable boundaries of conventional observation into realms where mathematics becomes our most reliable guide. Dr. Ashtakar's team at Penn State has developed computational models that simulate the quantum bounce process in extraordinary detail, revealing how information flows across the transition from collapse to expansion. These simulations show something remarkable about the nature of causality itself. In classical general relativity, the singularity represents a breakdown not just of matter and energy, but of cause and effect. Past and future become meaningless concepts at a point of infinite density. But in the quantum bounce scenario, causality threads through the transition in subtle, beautiful ways that preserve the logical structure of physical law while transforming its expression. Picture information as a river flowing through the cosmic landscape. In the classical model, this river encounters an infinite waterfall where all meaning disappears. But quantum effects create what we might think of as a tunnel through the mathematical cliff, allowing the river of causality to continue flowing into new territory on the other side. The information that describes matter, energy, and the relationships between them doesn't vanish at the bounce, but transforms according to quantum mechanical principles that we're only beginning to understand. Dr. Francesca Vidotto's work at the University of the Basque Country has revealed how quantum entanglement patterns established during the collapse phase persist through the bounce and into the expanding phase. These correlations create what she describes as quantum memories embedded in the very structure of spacetime. The universe carries within its geometric fabric the imprint of its pre-bounce existence, like fossil traces of the cosmic ecosystem that preceded our current reality. The mathematics describing these quantum memories are hauntingly beautiful. They suggest that the large-scale structure of our universe, the cosmic web of matter and energy that connects galaxies across billions of light years, might reflect correlation patterns established during our cosmos's birth within a black hole. Every filament of dark matter, every void between galaxy clusters, could be encoding information about physical processes that occurred in the parent universe before our reality began. Recent observations from the Dark Energy Survey have mapped the cosmic web with unprecedented precision, revealing structural patterns that align remarkably well with predictions from bounce cosmology. The way matter organizes itself on the largest scales shows subtle but persistent correlations that extend across distances so vast that light hasn't had time to travel between them since the Big Bang. These correlations make sense if our universe began as a single, highly connected system that then expanded while preserving its quantum relationships. The philosophical implications of quantum memory in spacetime touch on fundamental questions about the nature of history and identity. If our universe carries encoded information about its pre-existence, then the familiar notion of the Big Bang as an absolute beginning requires revision. We might inhabit not a cosmos born from nothing, but a reality that represents the continuation of processes that extend far back into a larger cosmic history. Dr. Carlo Rovelli's work on the relational interpretation of quantum mechanics provides a framework for understanding how these quantum memories might manifest in physical reality. According to his approach, information doesn't exist in abstract mathematical spaces, but emerges from the relationships between physical systems. The quantum correlations that survive the bounce wouldn't be stored in some cosmic database, but would express themselves through the ongoing interactions between matter and energy throughout our universe. This relational perspective transforms how we think about the connection between our universe and whatever larger reality might contain it. Rather than existing in complete isolation within a black hole, our cosmos might maintain subtle, informational relationships with its parent universe through quantum channels that transcend the classical boundaries of event horizons. The mathematics of quantum mechanics allows for correlations that persist even when direct communication becomes impossible. The experimental search for these quantum relationships has led to some of the most sophisticated measurements in the history of science. The European Space Agency's Planck mission spent years mapping the cosmic microwave background radiation with extraordinary precision, looking for patterns that might reveal our universe's quantum origins. The data shows subtle temperature fluctuations that follow statistical distributions consistent with quantum bounce predictions. These fluctuations aren't random noise, but carry information about the quantum processes that shaped our universe's birth. Like fingerprints left by the bounce event, they provide a record of how matter and energy behaved during the transition from collapse to expansion. The patterns are incredibly faint, requiring years of careful analysis to extract from the cosmic background, but they represent potentially the most direct evidence we have for our universe's exotic origins. Dr. Abhay Ashtekar describes the search for these quantum signatures as archaeological work conducted on cosmic scales. Just as archaeologists piece together ancient civilizations from scattered artifacts, cosmologists are reconstructing the story of our universe's birth from traces embedded in the fundamental structure of space and time. Each new observation adds another piece to a puzzle that spans scales from quantum to cosmic. The James Webb Space Telescope has revolutionized this cosmic archaeology by revealing the universe's earliest epochs with unprecedented clarity. The ancient galaxies Webb observes formed when our cosmos was young, their light carrying information about the physical processes that shaped the early universe. The patterns of star formation, the distribution of heavy elements, even the shapes and sizes of primordial galaxies, all provide clues about whether our universe emerged from a quantum bounce. What Webb sees challenges traditional Big Bang models in subtle but significant ways. The early universe appears more organized and structured than smooth initial conditions would predict. Massive galaxies with complex morphologies existed earlier than should have been possible if the cosmos began from perfectly uniform density. These observations find natural explanation in bounce cosmology. where pre-existing structure from the collapse phase provides seeds for rapid organization during the expansion phase. The technological challenges of probing our universe's quantum origins push the boundaries of human ingenuity. Dr. Rana Adhikari's team at LIGO has achieved sensitivities that approach the fundamental quantum limits of measurement, detecting gravitational waves from black hole mergers occurring billions of light years away. These observations provide direct information about how spacetime behaves under the extreme conditions that might characterize universe-creating bounces. Future gravitational wave observatories planned for space deployment will achieve even greater sensitivities, potentially revealing the quantum texture of spacetime itself. The laser interferometer. Space antenna, when fully operational, will be capable of detecting gravitational waves across a vast range of frequencies and intensities. If our universe truly originated from a quantum bounce, these instruments might detect the gravitational echoes of that primordial event still reverberating through the fabric of space and time. The mathematical framework describing these possibilities continues to evolve as researchers discover new connections between quantum mechanics, gravity, and information theory. Dr. Ted Jacobson at the University of Maryland has shown that Einstein's equations of general relativity can be derived from thermodynamic principles applied to event horizons. This suggests a deep relationship between gravity, information, and entropy that might explain how black holes can give birth to new universes. Jacobson's approach treats spacetime not as a fundamental entity, but as an emergent property of more basic information processing systems. Just as temperature emerges from the statistical behavior of countless molecules, the geometry of spacetime might emerge from quantum correlations operating at scales far smaller than we can directly observe. This emergence paradigm provides a natural framework for understanding how universes might arise from the information processing that occurs within black hole interiors. The implications for consciousness and the nature of mind become particularly intriguing when viewed through this lens. If spacetime itself emerges from information processing, then the boundary between mental and physical phenomena becomes far more fluid than traditionally assumed. Consciousness might not be something that emerges from complex arrangements of matter, but rather a fundamental aspect of how information organizes itself into increasingly complex patterns. Dr. Chris Fields at the University of New Mexico has explored these connections in remarkable depth, showing how the principles of quantum information theory apply to cognitive processes and conscious experience. His work suggests that the same mathematical structures governing black hole physics might also describe how awareness emerges from neural activity. The quantum correlations that create spacetime might be intimately related to the quantum processes that generate conscious experience. This creates a picture where consciousness and cosmos are expressions of the same underlying information processing principles. Your thoughts right now, contemplating these cosmic possibilities, might be participating in the same fundamental processes that created our universe within a black hole, and that continue to shape the evolution of space and time themselves. Every moment of awareness becomes a microcosm of the creative processes operating throughout the cosmic hierarchy. The recursive nature of these relationships suggests that consciousness might naturally tend toward cosmic understanding. The capacity to ask questions about our origins and place in existence might be an inevitable consequence of information processing systems achieving sufficient complexity and self-reference. Our wonder about black hole universes and nested realities might reflect the universe's own drive towards self-understanding, expressing itself through conscious beings. Dr. Giulio Tononi's integrated information theory provides mathematical tools for quantifying consciousness and its relationship to physical systems. His framework suggests that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond the sum of its parts. Applied to cosmic scales, this principle might explain how universes within black holes develop the capacity for self-awareness through the conscious beings they contain. The search for other conscious systems within our universe takes on new meaning in this context. If consciousness emerges naturally from information integration at sufficient scales, then the cosmos might be teeming with forms of awareness we haven't yet learned to recognize. The supermassive black holes at galactic centers, processing enormous amounts of information through their accretion disks and relativistic jets, might represent cosmic-scale conscious systems operating according to principles we're only beginning to glimpse. Even more intriguingly, the black holes within our universe might harbour their own conscious civilizations, beings who contemplate their origins just as we do, perhaps arriving at similar conclusions about existing within nested hierarchies of reality. The isolation imposed by event horizons means we can never communicate directly with such civilizations, but the mathematical universality of physical laws suggests they might discover the same fundamental principles we're uncovering. The possibility of consciousness operating at multiple scales throughout the cosmic hierarchy transforms our understanding of intelligence and purpose. Rather than being rare accidents in an otherwise unconscious universe, aware beings might be natural expressions of cosmic information processing. Every level of reality, from quantum to galactic, might develop its own forms of consciousness, adapted to its particular scales and physical conditions. Dr. Max Tegmark's work on the relationship between mathematics and consciousness suggests even deeper connections between mind and cosmic structure. His research indicates that conscious systems naturally evolve toward mathematical understanding because mathematics represents the most efficient way to compress and process information about reality. Our mathematical discoveries might reflect not just human cleverness, but the universe's own mathematical nature, expressing itself through conscious exploration. This mathematical universe hypothesis takes on profound new dimensions when combined with black hole cosmology. If our universe exists within a black hole described by mathematical relationships, then our mathematical understanding represents a form of cosmic self-recognition. Through conscious beings like ourselves, the universe achieves awareness of its own mathematical structure and relationships. The beauty of mathematical relationships in physics, from the elegant simplicity of E equals mc squared to the complex symmetries of quantum field theory, might reflect the aesthetic preferences of cosmic information processing systems. What we experience as mathematical beauty might be our recognition of the universe's own aesthetic sensibilities, patterns that please conscious systems because they represent optimal solutions to information processing challenges. The contemplation of these possibilities brings us to questions that transcend traditional scientific inquiry, touching on issues of meaning, purpose, and the nature of existence itself. If we truly inhabit a universe born from a black hole bounce, contained within layers of cosmic hierarchy that extend infinitely in both directions, what does this mean for human significance and cosmic purpose? One perspective suggests profound humility. In an infinite hierarchy of nested realities, our universe becomes vanishingly small, our planet an invisible speck, our individual lives mere fluctuations in cosmic information processing. Yet another perspective reveals extraordinary significance. If consciousness represents the universe's method of understanding itself, then every moment of awareness contributes to cosmic self-knowledge. Our contemplation of these mysteries participates directly in the fundamental processes by which reality explores its own nature. The resolution of this paradox might lie in recognizing that significance doesn't depend on scale, but on participation. Regardless of whether we exist at the base level of reality or within infinite layers of holographic projection, our capacity to experience wonder, to ask questions about existence, to create meaning through relationship and understanding remains precious and irreplaceable. Dr. Freeman Dyson spent his final years contemplating these questions about consciousness and cosmic purpose. His work suggested that intelligence might be a fundamental feature of the universe, destined to spread throughout the cosmos and eventually influence cosmic evolution itself. In a hierarchy of black hole universes, this intelligence might operate at every level, with each conscious civilization contributing to the ongoing creative process that generates new realities. The prospect of consciousness participating in cosmic creation represents perhaps the ultimate expression of intelligence and creativity. If we could eventually understand the quantum processes that create universes within black holes, we might develop the ability to influence or even initiate such processes. Conscious beings would become not just observers of cosmic evolution, but active agents in the ongoing creation of existence itself. The ethical implications of such possibilities challenge us to think about responsibility and stewardship on scales that dwarf any previous human concern. What obligations would we have to potential conscious beings within universes we might create? How would we ensure that our creative capabilities served the flourishing of awareness and meaning throughout the cosmic hierarchy? These questions may seem impossibly remote from everyday human concerns, yet they emerge naturally from following the mathematical logic of our current understanding. The same quantum mechanical principles that govern atomic behavior also describe the bounce processes that might create universes. The same general relativistic equations that predict GPS satellite corrections also describe the curvature of spacetime within black holes. The unity of physical law across all scales suggests that questions about cosmic consciousness and universe creation aren't merely philosophical speculation, but natural extensions of scientific inquiry. As our understanding of quantum gravity advances, as our observational capabilities expand, as our theoretical frameworks become more sophisticated, these questions will likely transition from speculation to active research programs. The timeline for such developments might span decades or centuries, requiring advances in technology and theory that we can barely imagine. Yet the mathematical foundations already exist, encoded in the equations of quantum mechanics and general relativity. The universe has provided us with the tools needed to understand our cosmic context. We need only develop the wisdom and capability to use them. As we drift toward the conclusion of tonight's journey through nested realities and cosmic consciousness, we find ourselves transformed by the contemplation of possibilities that stretch far beyond everyday experience. The familiar world of solid objects and definite locations reveals itself as just one layer in an infinitely complex hierarchy of information processing and conscious experience. The gentle rhythm of your breathing connects you to cycles that span from quantum fluctuations to cosmic expansion. Each heartbeat participates in information processing networks that might extend through dimensions we cannot directly perceive. Your thoughts, contemplating these cosmic mysteries, might be contributing to patterns of self-understanding that operate at the scale of the universe itself. The mathematical beauty of these relationships suggests that wonder and curiosity aren't accidental features of consciousness, but fundamental aspects of how information organizes itself into increasingly complex and self-aware systems. The questions we ask about black hole universes and nested realities might be expressions of the cosmos's deepest drive toward understanding and meaning-making. In the soft transition between waking thought and dreaming consciousness, these ideas take on a different quality. The boundaries between self and universe, between mind and matter, between the observer and the vast hierarchy of nested realities, dissolve into more fluid patterns of connection and relationship. You drift now through information spaces that extend far beyond ordinary dimensions, carried by currents of possibility that connect every moment of awareness to the fundamental creative processes of existence. The darkness that surrounds you isn't empty space, but a rich tapestry of quantum correlations and holographic encodings that might extend through infinite layers of reality. Each thought that forms in response to these contemplations participates in the universe's ongoing conversation with itself, adding new patterns of meaning to the computational substrate that gives rise to consciousness, complexity, and the endless capacity for wonder that makes existence so extraordinarily beautiful and mysterious. Whether we exist at the fundamental level of reality or within infinite hierarchies of black hole universes, our capacity to contemplate these possibilities remains one of the most precious features of the cosmos we call home. In this liminal space where science meets wonder, where mathematics touches mystery, where individual consciousness encounters cosmic intelligence, we discover that the universe is not just stranger than we imagine, but more magnificent than we have yet dared to dream. The story becomes even more extraordinary when we consider the work being conducted in laboratories and observatories around the world, where researchers are pushing the boundaries of what we thought possible about the nature of reality itself. At the heart of these investigations lies a question that has haunted physics for decades. What happens when the equations that describe our universe encounter infinities? Dr. Abhay Ashtakar's laboratory at Penn State resembles something between a monastery and a mission control center. Here, amid walls covered with equations that stretch from floor to ceiling, some of the world's most brilliant minds spend their days wrestling with mathematics so complex that each calculation requires months of careful verification. They're working on what might be the most important problem in theoretical physics, understanding what occurs at the moment when space and time themselves break down. The classical picture of gravitational collapse paints a stark and troubling portrait. When matter compresses beyond a certain critical density, the mathematics of Einstein's general relativity predict something that makes physicists deeply uncomfortable, a point where density becomes infinite, where the curvature of spacetime becomes infinite, where the very concept of physics ceases to have meaning. These singularities represent not just mathematical curiosities, but fundamental breakdowns in our understanding of how reality operates. Yet Ashtakar's team has discovered something remarkable hidden within the equations of quantum gravity. When they incorporate the discrete, granular nature of space and time at the smallest scales, the infinite compression that classical physics predicts simply cannot occur. Instead, matter reaches a maximum density and then rebounds with tremendous force, creating new expanding spacetime in the process. The mathematics are elegant and precise, describing how what appears to be the end of everything becomes the beginning of something entirely new. Picture the process unfolding across timescales that dwarf human comprehension. In the parent universe, a massive star reaches the end of its nuclear burning lifetime. The delicate balance between outward radiation pressure and inward gravitational pull collapses in seconds. Matter compresses toward densities that exceed anything found elsewhere in nature. But just when classical physics would predict catastrophic breakdown, quantum effects intervene with subtle yet overwhelming power. The fundamental particles that comprise this collapsing matter begin to resist further compression through mechanisms encoded in the deepest laws of quantum mechanics. The Pauli exclusion principle, that elegant rule preventing identical particles from occupying the same quantum state, creates pressures that eventually overcome even the immense gravitational forces driving the collapse. Rather than infinite compression, the matter reaches a turning point and begins to expand again. From the perspective of observers in the parent universe, this process might unfold over eons, stretched by gravitational time dilation near the event horizon. But from within the newly forming universe, this rebound appears as the explosive expansion we call the Big Bang. The rapid inflation that shapes our cosmic architecture, the synthesis of light elements that provides the chemical foundation for stars and planets, even the mysterious dark energy driving our universe's accelerating expansion, all emerge naturally from this quantum bounce. Dr. Lee Smolin at the Perimeter Institute has extended these insights into a comprehensive theory of cosmic evolution. His work suggests that universes might reproduce through black hole formation, with each new universe inheriting slightly modified physical constants from its parent. Over countless generations of cosmic reproduction, this process would naturally select for universes capable of producing complex structures, including the stars, planets, and ultimately the conscious beings needed to continue the cycle. The elegance of this evolutionary cosmology lies in how it explains the apparent fine-tuning of physical constants without requiring external design or infinite multiverse scenarios. Our universe's properties, from the strength of gravity to the mass of elementary particles, might represent the accumulated wisdom of countless cycles of cosmic natural selection. We inhabit a universe whose physical laws have been refined through eons of evolutionary pressure toward complexity and consciousness. Recent observations have provided tantalizing support for these radical ideas. The cosmic microwave background radiation, that ancient afterglow of our universe's hot, dense beginning, shows patterns that align remarkably well with predictions from bounce cosmology. The tiny temperature fluctuations that eventually grew into galaxies and galaxy clusters follow statistical distributions that match what quantum bounce models predict. Even more intriguingly, observations from the James Webb Space Telescope have revealed that the early universe was far more organized and structured than traditional models suggest. Massive galaxies with complex morphologies existed earlier than should have been possible if our cosmos began from perfectly smooth initial conditions. These observations find natural explanation if our universe inherited pre-existing structure from the collapse phase that preceded the bounce. Dr. Carlo Rovelli's work on loop quantum gravity has revealed the discrete atomic structure of space and time themselves. At scales trillions of times smaller than atomic nuclei, spacetime becomes granular, composed of tiny loops and networks that give geometry its quantum mechanical foundation. This discreteness provides the mechanism that prevents singularities from forming, ensuring that collapsing matter bounces rather than disappearing into mathematical abstraction. The implications ripple through every aspect of our understanding of cosmic evolution. The formation of the first atoms, the ignition of primordial stars, the assembly of galaxies into the cosmic web we observe today, all occur within the context of a universe whose initial conditions were shaped by processes that operated in another reality entirely. We are not just products of our own cosmic history, but inheritors of evolutionary pressures that span multiple levels of reality. The mathematical frameworks describing these processes draw from some of the most advanced areas of theoretical physics. String theory provides tools for understanding how fundamental particles behave during the extreme compression and expansion phases. Loop quantum gravity reveals how spacetime itself maintains coherence during the transition. The holographic principle suggests how three-dimensional realities can emerge from information processing on two-dimensional boundaries. These theoretical advances are occurring alongside revolutionary improvements in observational capability. Gravitational wave observatories like LIGO and Virgo have opened entirely new windows into the behavior of spacetime under extreme conditions. When black holes merge in distant regions of our universe, they create ripples that carry information about the fundamental nature of gravity and quantum mechanics. The patterns these instruments detect in gravitational waves provide indirect evidence about the processes that might create new universes within black hole interiors. The way spacetime responds to extreme compression and acceleration reveals details about quantum geometry that would be impossible to study through any other means. Each detected merger adds another piece to our understanding of how reality behaves when pushed to its absolute limits. Future gravitational wave observatories planned for space deployment will achieve sensitivities that approach the quantum limits of measurement itself. These instruments might detect the subtle signatures of universe creation within black holes, revealing the quantum processes that transform collapsing matter into expanding spacetime. Such observations would provide the most direct evidence possible for our own cosmic origins within a larger hierarchy of nested realities. The prospect of observing universe creation in progress represents one of the most thrilling possibilities in modern science. If we could detect the quantum signatures of the bounce process occurring within black holes in our own universe, we would witness the birth of entirely new realities, complete with their own space, time, and potentially their own forms of consciousness. The technological challenges are immense, requiring advances in precision measurement that push against the fundamental limits imposed by quantum mechanics itself. Yet the scientific rewards would justify even the most ambitious investments. Direct observation of cosmic birth would rank among the greatest discoveries in human history, revealing the deepest mechanisms by which existence generates new layers of reality. Dr. Raul Carballo Rubio's research at the International Center for Theoretical Physics has revealed that these universe-creating processes might be far more common than previously imagined. His calculations suggest that every black hole, from stellar mass objects formed by collapsing stars to the supermassive behemoths lurking at galactic centers, could potentially harbor expanding universes within their interiors. This creates a picture of existence that is both humbling and awe-inspiring. The Milky Way galaxy alone contains millions of black holes, each potentially sheltering entire cosmos, teeming with stars, planets, and possibly conscious civilizations. Our observable universe, vast as it appears to us, might be just one member of an infinite community of nested realities, each as rich and meaningful as any other. The philosophical implications challenge every assumption about significance and purpose. In an infinite hierarchy of nested universes, questions of scale and importance require complete reconceptualization. Perhaps meaning doesn't derive from being large or fundamental, but from participating in the ongoing creative processes that generate complexity, consciousness, and the capacity for wonder itself. The recursive nature of these relationships suggests that every level of reality contributes something unique to the cosmic conversation. Our scientific discoveries, our artistic creations, our moments of love and understanding, all add patterns of meaning to the vast information processing system that gives rise to conscious experience throughout the hierarchy. Individual significance emerges not despite our cosmic context, but because of our participation in processes that extend far beyond any single universe. Dr. Leonard Suskind's work on the holographic principle reveals how three-dimensional realities like ours might emerge from information processing occurring on distant two-dimensional boundaries. This isn't mere mathematical abstraction, but a fundamental insight into how information, space, and time relate to one another at the deepest levels of reality. If our universe truly operates according to holographic principles, then every star you see in the night sky, every planet orbiting distant suns, every thought forming in your mind right now, represents the projection of computational processes occurring on surfaces we can never directly observe. This doesn't make our reality less real or meaningful, but suggests that the relationship between information and physical existence might be far more subtle and beautiful than we ever imagined. The search for experimental verification of these ideas continues to push the boundaries of human ingenuity and technological capability. Teams around the world are developing increasingly sensitive instruments capable of detecting the quantum signatures that would confirm our universe's holographic nature. The patterns they seek are incredibly faint, requiring years of careful observation and analysis to extract from cosmic background noise. Yet the convergence of evidence from multiple independent sources continues to build a compelling case for this radical reimagining of our cosmic context. Gravitational wave observations, cosmic microwave background studies, investigations of black hole physics, and theoretical advances in quantum gravity all point toward the same stunning conclusion. We might indeed inhabit a universe born from quantum processes within a black hole, formed in some larger parent reality. The mathematical beauty of these relationships suggests that wonder and curiosity aren't accidental features of consciousness, but fundamental aspects of how information organizes itself into increasingly complex and self-aware patterns. Our contemplation of these cosmic mysteries might represent the universe's method of achieving self-understanding through the conscious beings it has somehow managed to create. In laboratories and observatories around the world, researchers continue their patient investigation of these profound questions. Each new observation, each theoretical breakthrough, each mathematical insight adds another piece to humanity's growing understanding of our place in the cosmic hierarchy. Whether we exist at the fundamental level of reality or within infinite layers of nested universes, our capacity to ask these questions remains one of the most remarkable features of existence itself. The gentle progression from day into night that surrounds you as you contemplate these ideas connects you to cycles that span from quantum oscillations to cosmic expansion. Your breathing synchronizes with rhythms that might extend through dimensions beyond ordinary perception. Each thought that forms in response to these contemplations participates in information processing networks that could encompass scales from subatomic to universal. The darkness gathering around you isn't empty space, but a rich medium filled with quantum fields and curved geometries that might extend through hierarchies of reality we're only beginning to glimpse. In this quiet transition between the familiar world of everyday experience and the vast mystery that contains it all, the boundaries between observer and observed, between individual consciousness and cosmic intelligence, become beautifully permeable. Tonight, as your awareness drifts toward the threshold where waking thought meets the quantum realm of dreams, you touch something infinite and eternal. The questions we've explored together don't have final answers, but they open doorways to ever deeper appreciation of the magnificent mystery in which we find ourselves embedded. Whether we inhabit the base level of reality or exist within endless layers of cosmic nesting, our capacity to wonder about these possibilities remains precious beyond measure. The mathematical equations that describe black hole formation and quantum bounces operate according to principles that transcend any particular universe or level of reality. This universality suggests that conscious beings throughout the cosmic hierarchy might discover the same fundamental relationships, ask similar questions about their origins and destiny, and perhaps even arrive at the same stunning realization that they too might exist within black hole universes contained in even larger parent cosmos. The story continues to unfold in research institutions around the globe, where the next generation of scientists is developing tools and techniques that would have seemed impossible just decades ago. Their work represents humanity's ongoing participation in the universe's exploration of its own nature, adding our unique perspective to the vast conversation that consciousness conducts with itself across all scales of existence. In the gentle space between one breath and the next, in the soft transition from certainty to wonder, from individual awareness to cosmic consciousness, we discover that the universe is not just stranger than we imagine, but more magnificent and interconnected than we have yet dared to dream. The mystery deepens with every answer we find, revealing infinite layers of beauty and meaning that extend far beyond the boundaries of any single reality, any individual mind, any moment in the endless dance of existence exploring itself through countless forms of consciousness and wonder. As we approach the culmination of our cosmic journey. Tonight, we find ourselves standing at the edge of perhaps the most profound realization in all of science. The equations we've explored, the observations we've examined, the theoretical frameworks we've traversed, all converge toward a single, breathtaking possibility that challenges every assumption we've held about the nature of existence itself. The mathematics tell a story that reads like poetry written in the language of the universe. When Dr. Nikodym Poplawski first derived the solutions to Einstein-Cartan field equations that describe matter behavior under extreme gravitational compression, he discovered something that would forever change how we think about cosmic origins. His calculations revealed that the quantum properties of matter create a natural resistance to infinite compression, a resistance so fundamental that it operates at the very core of physical reality. Imagine matter compressed to densities so extreme that the familiar concepts of solid, liquid, and gas become meaningless. At these densities, roughly 100 million trillion times greater than water, the building blocks of reality itself begin to push back with a force that emerges from the deepest principles of quantum mechanics. This isn't the mechanical resistance of springs or steel, but something far more profound, the universe's own refusal to allow itself to collapse into nothingness. The beauty lies in the simplicity of what happens next. The same quantum exclusion principle that prevents electrons from crashing into atomic nuclei, that gives matter its structure and stability, scales up under these extreme conditions to become the force that prevents cosmic collapse. When compression reaches its maximum possible density, the universe doesn't end in mathematical abstraction, but transforms, rebounds, and begins to expand again with tremendous creative force. From our perspective within this expanding system, this quantum rebound appears as the moment we call the Big Bang. Every galaxy spiraling through space, every star burning in the cosmic night, every atom in your body, all emerged from this primordial bounce that occurred when our parent universe's matter reached the point where quantum mechanics said, "No further," and reversed the tide of gravitational collapse. The experimental evidence supporting this radical reimagining continues to accumulate in ways that would have seemed impossible when Einstein first wrote his equations. The Planck satellite's exquisite mapping of the cosmic microwave background revealed temperature fluctuations that follow precisely the statistical patterns that bounce cosmology predicts. These aren't random variations in ancient light, but quantum fingerprints left by the rebound process that created our cosmic home. Recent gravitational wave detections have opened entirely new channels for probing the fundamental nature of spacetime itself. When LIGO and Virgo detect the ripples created by merging black holes, they're revealing how the fabric of reality responds to the extreme conditions that might characterize universe-creating bounces. Each detection adds another piece to our understanding of how quantum geometry operates under conditions we can barely comprehend. The James Webb Space Telescope has revolutionized our view of cosmic dawn, revealing galaxies that existed when our universe was young. These ancient stellar cities show levels of organization and complexity that traditional Big Bang models struggle to explain, but which emerge naturally if our cosmos inherited structure from the collapse phase that preceded the bounce. We're seeing the archaeological evidence of our universe's pre-existence encoded in the patterns of primordial light. Tonight, as you prepare to drift into sleep, carry with you this extraordinary possibility that we've explored together. Whether our universe exists within a black hole or represents some fundamental level of reality, the very fact that matter has organized itself into patterns capable of contemplating these cosmic mysteries remains one of the most remarkable features of existence itself. In questioning our origins, in wondering about nested realities and quantum bounces, we participate in the universe's ongoing conversation with itself. Rest well, knowing that you're both observer and participant in this magnificent cosmic story that continues to unfold with each moment of conscious wonder.